Hi, I'm Katie McCullough from the Ed Institute team. And in this video, I'm going to discuss different ways to visualize inequalities as comparisons between quantities. Inequality symbols express comparisons. They give us a shorthand way to express that some quantity has a greater or lesser value than some other quantity. When used to compare numbers, this is very concrete. These symbols give us a way to represent that 5/8 is greater than 4/7, and that -2 is greater than -6. But let's take a look at what happens when the quantities that we are comparing involve values that can vary, or variables. For example, the inequality 2x plus 3 is less than 7 tells us that 3 more than double some values gives me an amount less than 7. Because x can vary, 2x plus 3 will not always be less than 7, but there is some set of x values that does make this comparison true. Solving an inequality means finding that set of values, called the solution set. If I picture these quantities on two sides of a scale or a balance, then I can picture the scales tipping as I change the value of x. Finding the solution set means finding all of the values of x that tip this scale so that 7 is heavier than 2x plus 3, pulling the scale down on the right side. When I look at 2x plus 3, I see that increasing the value of x will increase the value of 2x, and adding 3 just increases that more. As I increase x, I can picture the left side of the scale getting heavier and heavier and getting pulled down more and more. But as I decrease x, the value of 2x plus 3 decreases. So I can picture the left side of my scale rising as it gets lighter and lighter. To get more precise than this, I can look inside of these amounts. 2x plus 3 is made up of 2 x's and 3 1's. 7 is made up of 7 1's. On both sides of my scale, I can now see 3 1's. Those 3 1's always have the same weight or value, so they are not tipping the scale one way or another. That means that the other pieces of these quantities, the 2 x's on the left and the 4 1's on the right, those are what tips the scale one way or another. When 2x is exactly equal to 4, then the scale is perfectly balanced, and 2x will have the same value as 4 when x equals 2. But when we change the value of x ever so slightly, then the scales will start to tip one way or the other. If we decrease the value of x by any amount, even by 1/10,000th or 1/1,000,000th, then the scale will tip to the right, towards 7. So that means for all values of x less than 2, no matter how close they get to 2, 2x plus 3 will be less than 7. The solution set is x is less than 2, or all values less than 2. Because 2x plus 3 is a quantity that can vary, this inequality describes a comparison that is true for an entire set of values. We were able to determine which values by looking inside of 2x plus 3 and 7 to determine which parts of these amounts account for the differences in their values. Let's take a look at what happens when we compare two quantities that can vary. 2x plus 3 is less than 3x plus 2. Though comparing two quantities that can vary is more abstract because both the value of 2x plus 3 and the value of 3x plus 2 change as x changes, I can still compare these expressions in the same way that I did before. When I picture this inequality again as a scale, the solution set will be all values of x that tip the scale so that 3x plus 2 is heavier than 2x plus 3. Just like when I compared 2x plus 3 to 7, I am going to look inside of each expression to identify which pieces are the ones that tip the scales one way or another. I know that the quantity 2x plus 3 is made up of 2 x's and 3 1's, and I know that the quantity 3x plus 2 is made up of 3 x's and 2 1's. I can see 2 x's and 2 1's on both sides of my scale or my balance. Even though the value of x can change, it has the same value or the same weight in both expressions. Just like the 2 1's are contributing the same value or weight to each expression, the 2 x's are as well. So these 2 x's and 2 1's cannot possibly tip the scale one way or another. The only objects that can tip my scale then are the remaining 1 on the left and the remaining x on the right. When x is equal to 1, then the two sides of the scale are exactly balanced. If we add any amount to x, even if it is just a tiny, tiny, tiny bit greater, then the scales will tip to the right. So any value greater than 1, no matter how close it is to 1, is in the solution set. X is greater than 1. Visualizing inequalities on a scale or a balance helped us make sense of these changing values by showing us which pieces of each expression were really responsible for the differences in their values. We can also use graphs to visualize how the values of 2x plus 3 and 3x plus 2 change as x changes. Graphs are only explicitly used as models for algebra in the grade 8 curriculum, but they are powerful tools to help us visualize how the value of each expression changes as x changes. Instead of looking inside of these expressions, as we did on the scales, graphs help us zoom out. Graphs show us the value that each expression has as an output for each different value of x, or each possible input. On this graph, this red line represents my first expression because it shows all y values or outputs that are 3 more than double the x value or input. This blue line represents my second expression. It shows y values that are 2 more than triple the corresponding x values. Looking back at our inequality, we want to see where the quantity 2x plus 3 is less than 3x plus 2. In other words, we want to use this graph to determine where the blue line is above the red line. This happens at every point to the right of x equals 1. If we think back to our scale, the scale will be perfectly balanced when these lines intersect at x equals 1, because that's where the same x value leads to the same total output value, or y value, for each expression. Then, as soon as x slides just past 1, the blue line is above the red line. I'm Katie McCullough. Through this video, I hope you have come to understand inequalities as comparisons between quantities. When these quantities can vary, it is important to visualize how the quantities change in relation to each other. Thanks for watching.